In this lecture, we will discuss the use of drugs to modulate the activity of enzymes. So let's do a quick recap of what enzymes are. Enzymes are proteins acting as catalysts in biological reactions. In this example, we look at lactate dehydrogenase, which is converting pyruvic acid to lactic acid. Pyruvic acid is the last product of glycolysis. When oxygen is absent, that's formed um, lactate, and that's basically what happens in the muscles, for example, during overexertion. Um, from the chemical point of view, the reaction we are looking at is the reduction of this ketone to a alcohol, and this reaction happens with formation of a chiral product, and it's so-called stereoselective. So we are forming only one of the two possible enantiomers of lactic acid. The reaction is formally a reduction and happens at the expense of NADH, which gets oxidized to NAD+. This is an enzyme, an overview of the structure. This is a heterodimer, and is composed of 4 subunits here colored in different colors. One important thing to remember, and you probably know already from biochemistry, is that lactic acid acts as an inhibitor and um, basically modulates the activity of lactate dehydrogenase so that the conversion of pyruvate of lactate is decreased when a lot of products is around. So how's that happening? What is the function of the enzyme exactly? As you will recollect from biochemistry and organic chemistry, the enzyme, just like any catalyst, lowers the energy of activation of a reaction, but does not really interfere with the delta G of the reaction, so the free energy difference of the reaction. In other words, they affect the kinetics, but not the thermodynamics of a reaction. And so this is the formula for the free energy, which is looking in this reaction coordinate as the difference in energy between starting products and starting material and products. What we are doing with the enzyme, and again with any catalyst, is lowering the energy of the transition state, and so facilitating the reaction, making it smaller. The energy of the transition state, or so-called activation energy, is this factor here, and so that comes up in the formula that describes the kinetics. In other words, the rate of the reaction. So let's look at the reaction and see how does an enzyme accomplish this task. How does it lower the energy of activation of the reaction? Well, there are several ways by which the enzyme acts, and all of them contribute in stabilizing the transition state. Specifically, the enzyme can provide a surface, the active site, in which there are suitable environment, basically side chains that can act as a reactant. The other function of the enzyme is to bring reactants together and positioning the reactant correctly for the reaction, and that is especially important in stereoselective reactions. Further, the enzyme will lower basically weaker bonds in the reactants and can provide also specific catalysis by specific amino acids that lie in the cavity, for example, acid-base catalysis or nucleophilic groups that can, in turn, carry out the reaction. Overall, this is the process. First, the substrate approaches the enzyme, then we have a binding process. The reaction then will happen on the enzyme-bound substrate. the product is released, and that's also a very important step. And sometimes there are more than one products released during this process. The amino acids lining the cavity can participate in substrate binding or can be part of the catalytic mechanism. Often they do both. The other way by which the enzyme acts is by changing the reaction coordinates, so changing the mechanism of the reaction slightly. In general, it is thought that substrate binding induce a different fit, so a different conformation in the enzyme, or stabilizes rather a different conformation of the enzyme. So the binding process can basically alter and strain some bonds in the substrate and facilitate the breaking of those bonds. Binding involves several intermolecular bonds between the functional groups in the substrate and also the functional group in the active site. So what kind of binding forces are involved? Let's see. We can have ionic bonding, hydrogen bonding, and van der Waals. So if we go back to our example of a pyruvic acid binding to lactose dehydrogenase, what we can see here is that we have a hydrogen bond component to the carbonyl group, and that hydrogen bonds happens with an alcohol moiety in the enzyme. We have hydrophobic interaction or van der Waals interactions here in the cavity between the methyl group and the surrounding environment. And we have ionic bonds between the carboxylates on pyruvic acid and a charged amine in the enzyme pocket. In general, the strongest interactions will be given by hydrogen bonding. And in general, hydrogen bonds happen to groups that can act as hydrogen bond donors or acceptors, so hydroxyl, amines, and other bonds. Less strong are dipole-dipole forces, and those are basically electrostatic interactions. And the weakest are London dispersion forces that underpin van der Waals interactions. So let's look at some examples of catalysis, and so let's look at the role that a few amino acids can have in catalysis. This is an example of acid-base catalysis, and one residue that is often at the base of this type of catalysis is histidine. Histidine has two forms: the non-ionized form, which can act as a base, and the ionized form, which can act as an acid. In other words, the non-ionized form can often abstract a proton from a substrate, whereas the ionized form can release that proton back to a substrate. So histidine is great in acid-base catalysis because it can accept or donate protons during a reaction mechanism. And this is very important because enzymes are typically quite hydrophobic, and there are very few water molecules present in the active site to carry out this role. Now let's look at another type of catalysis, the nucleophilic catalysis. And one example of a good nucleophile is a serine or cysteine. Let's see an example in the following slide of serine acting as a nucleophile. If we have a substrate with a good leaving group, X here, the lone pair on the oxygen of serine can attack the substrate, resulting in leaving of the leaving group, so minus X here. We now have a form in which the serine is covalently bound through this oxygen to the substrate, and then in the presence of a molecule of water, that complex gets released, and so we repristinate the serine, and we free up the product, which gets released in the environment. So one thing to notice is that serine is unchanged during the reaction, which is one of the definition of a catalyst. And the catalyst is not involved in the reaction. Well, it is involved, but doesn't get altered in the reaction. So let's look at the very common mechanism for many proteases, which are based on a catalytic triad of serine, histidine, and aspartate. And here we will see our example amino acids, serine and histidine, act in the two roles. So first, the mechanism by which chymotrypsin can break a bond relies on these two amino acids mainly. Chymotrypsin are proteases, and so they will break this amide bond in a protein. This happens by first having the nucleophilic attack of a serine to the protein, the carbonyl of the protein, and so the protein is held in place by the rest of the enzyme. So in the first step, we form this tetrahedral intermediate, which then gets deprotonated by a nearby histidine, part of the catalytic trial. We form now this covalent adduct to the enzyme, which then rearranges, and so we have a lone pair from the oxygen here of the alkoxy group, getting back to form double bond again. That happens with breakage of the carbon-nitrogen bond. Normally, that's a very difficult reaction, so hydrolysis of amide bonds is not easy and requires extreme conditions in organic chemistry, but that's exactly what the enzyme does. It stabilizes the protein and positions the bond to be broken just right so that the reaction can take place. As the amine group is released, it gets protonated by these nearby histidines that had been protonated in previous step. So now we have release of protein NH2. We are now left with a covalent adduct to the enzyme where the other half of the protein is still linked through an ester linkage to the serine. And now that ester gets resolved by using a water molecule which attacks the carbonyl bond, and so we have once again formation of a protonated tetrahedral intermediate. The intermediate now gets deprotonated by the histidine in the catalytic trial, and then we form this geminal dialkoxide, where now the negative charge, so the lone pair on the oxygen, forms back the double bond that happens with release of the alcohol here, which gets protonated by the histidine as it leaves. And so we repristinate the alcohol on serine, release the C-terminus of the protein, and the rest of the catalytic trial is found as first. So the presence of this nucleophilic serine really means that the water is not required in the initial stage of the reaction, and that's very important. So just to summarize, what are the overall steps of enzyme catalysis? We have enzyme binding a substrate to form the enzyme substrate complex that gets converted to enzyme product, and then we have release of product in the last step.